Good afternoon and good morning, everyone. This is Senthil Kumar. I'm a program manager at Hillphoenix, work for Center of Excellence for CO2. So today in this session, we are going to look into like a few topics, which is CO2 overview, why CO2, and how it helps to transition into natural refrigerant solution. And then typical current CO2 booster system design pressures. We are going to go over the pressures, like how the CO2 works, what are the design pressures on the suction side and discharge side, and what is the typical pressure of the overall system. And then we are going to go through the increased pressure assessment. What happens when there's a power loss or there is a service event happening? What happens to CO2 and how the pressure increases and how to mitigate that? So the last one is like how to, like approach to manage the increased pressures within the system. So this is the basic overview of this, today's session. So feel free to put your questions on your chat and then we can answer at the end. So to start with CO2 overview, why CO2 as a refrigerant to start with? So this, like push to move away from HFC refrigerant. That's one of the regulations is coming up based on the AIM Act. And CO2 is an environment-friendly refrigerant, right? So it has a ODP of 0, which is ocean depletion potential of 0, and the global warming potential, GWP, is 1 for CO2 when compared to HFC refrigerant. So the other HFC refrigerant, GWP, starts from 1800 and it goes all the way to like 3000 to 4000, but CO2 is like 1. So which is natural. So we breathe in oxygen and breathe out CO2. And CO2 is available in the environment, and trees breathe in CO2 and breathe out of, like oxygen. So it's a natural refrigerant. It's a non-toxic and it's classified as a A1 refrigerant by ASHRAE. So, and then if you look at the cooling capacity of CO2 when compared to HFC refrigerant, it has a higher cooling capacity, which is thermal efficiency basically. So for if you look at the screen, it says like BTU per pounds stored load. If you look at CO2, it produces, or the cooling capacity of CO2 is like 100.5 per pounds of CO2 refrigerant when compared to HFC. Other HFCs, the BTU per pound of refrigerant is like ranges from 42 to 60 or 68. And the ammonia is the highest one, which is, 458 BTU per pounds. So CO2 is a natural refrigerant and it has a high cooling capacity. It has a, like high coil efficiency, and you can design the system with a lower TD. So this also gives benefit natural, as I said, and it's compliant with the regulation, and it also allows us to avoid the future cost and energy efficient, as I said, and carbon emission reduction. Like every corporate retailers has their own ESG goals, environmental sustainable goals. It helps in reducing carbon emissions, and also it has no PFAS. As PFAS is, talk of the town in many places, and in Europe, there is a ban in PFAS. So for CO2, there is no, like issue or concern of going PFAS with going with the CO2. So that's why, like CO2 is a good refrigerant to go with as a future-proof solution for the retail industry and industrial markets.
Absolutely. So like
Yep.
in that, for CO2 wise, no forever chemicals, no
Yep.
cooling capacity is way more denser. We get way more out of it with smaller piping
Smaller
all
piping.
around,
Yes.
safe for the ozone, in the ozone, a lot of great benefits moving away from synthetic
Yes,
refrigerants.
yes, it's well said. Yes, that's correct. Yep. Yep. So next we will go over a little bit on the pressures, right? This is a pressure enthalpy diagram. So I do have the next slide coming up showing the schematics on the pressures, but now, like there are like 4 different pressures in the system, which is low temperature suction, subcritical, and then you have intermediate pressure, flash tank pressure, and then you have medium temp suction pressures. So 3 different pressures as shown in the, you know, pressure enthalpy diagram, and you have the medium temp discharge pressures. So, like in HFC systems, you have like 2 different pressures. If you take medium temp only or low temp only system, you have suction pressure and a discharge pressure. So there is no intermediate pressure. So that's one difference in CO2 system. So why we do that? To increase the COP of the system. by separating the flash gas. So that's the reason we do like a 4 different pressures. So you separate the flash gas and then you operate the, like you process the flash gas through medium term compressors or parallel compressors to improve the COP of the system. So there are 4 different pressures, and looking at the, like we call it as a subcritical, where you have a relationship between temperature and pressure. So when you increase the temperature, the pressure increases in the subcritical region. In the transcritical and the supercritical regions, where if you go up here, there is no relationship between the temperature and pressure. So that's different. So you can control the temperature separately and the pressure separately. So that's the, that's a property of the CO2. The critical point of CO2 is 87 degrees and about 1055 psi. And the liquid is operated under like 38 bar or 34 bar, depending upon the system design. So looking into the system design, how it's going to look like a typical CO2 systems around the world. And this is, in operation since 2011 or, even before that. So there are like 4 different pressures. One is medium temp suction, which is 45 bar, and then goes here as a medium temp discharge 130 bar design. And then coming back here, the flash tank pressure is 45 bar design pressure, and then the low temp suction is 30 bar design. So there are like 4 different design pressures. So what it means is like you operate your low temperature cases at -20, and typical operating is like 200 psi. And the relief valve is set to 30 bar on the low side. And if you go to the low temp discharge, and that is connected to your medium temp suction, the medium temp suction operates at +20 typically. The pressure is like 407 psi for +20, but the operating range, the maximum operating is like 45. And then if you go to discharge, medium term discharge, it will range from like 650 to 1660 operating range, but it is designed to 130 bar, 1885 psi. And then if you come back here, and then you have the high pressure valve. After the high pressure valve, you have the flash tank slash receiver, which is maximum design pressure on this design is like 45 bar, and then operating is like 35. So in typically we call this as medium term discharge 130, low temp discharge medium temp suction 45, and flash tank is 45, and the low temp suction is 30 bar. So we call this like 130, 45, 45, 30 bar system design. So
Just to break out the regions, just
the
break the
regions, yes,
sections of
sections.
cases where we'll have.
There are like 4 quadrants of the system, right? So that's
Right.
what we're going to see in the next slide. So why and how this is important. So more than like 70% of the system is designed within this pressure around the world today.
More than 70%.
Yeah, more than 70% is this design. So that's why we took this as an example to go through this so that everyone can understand easily. So next, we will go through what happens when there is a power outage. So sequence of events, right? So this is a typical system, and the first thing, when the power goes out, all the expansion valve close. So why it closes? So we use like a pulse valve. So pulse valve is a normally closed valves, right? So once you lose the power, the valve closes automatically. And there are cases we use like stepper valves, but when we use the stepper valves, we also put a liquid solenoid valves, because the stepper valves will not close automatically. It will stay in the step where it was originally. So the liquid solenoid valves closes. So that's the first step happens when you lose the power. The second step is the high pressure valve and the flash gas bypass valves will close. That is because we provide an UPS within the rack with a battery, and the control power is through UPS and the battery package. So the controller will drive these 2 valves to close. High pressure valve and the flash gas bypass valve will close. That's the second step happens. So by closing these valves, the system will divide into like a 4 quadrants. 4 sections, which is the first one is medium term discharge section. The red box here from the medium term compressor discharge going through the wall separator, gas cooler, and all the way up to high pressure valve. That's the quadrant 1. And then the second quadrant will be from high pressure valve and the flash gas bypass valve, flash tank, and all the liquid lines all the way up to the expansion valves on the low temp side and also on the medium temp side. So this will become a second quadrant or second section of the system. Yeah,
So in the kind of, for the recap for me, so not that it's like step one, step two, step three, because all this happens kind of
yes,
instantaneously.
it's
So
also all instance and
so,
yes,
but
yes,
what we want to do is we want to start sectioning off and breaking it down into these different quadrants.
yes,
So
yeah,
if we have pulse valves, we don't have to worry about, we don't have additional solenoid valves. Those, when they lose power, they're shutting.
shutting
They're
off.
locking off and they're done.
Yes,
If we have a EEV or something that's a step, it's a actual
stepper.
stepper motor,
Yep.
then we have to actually power that closed or have a solenoid take
So
control.
liquid
And
solenoid
solenoid
is
is the
also,
easiest way to do that,
yes, yeah,
right, without
yeah,
additional power.
yeah.
However, the high pressure control valve and the flash gas bypass valve, those are stepper motors. We
Stepper.
have to drive those closed
Yes, we
somehow.
don't have to go
So
this.
that's the main point. Like, once it happens, those
Yes.
shut off and then the UPS takes over and it closes those off.
Yes,
Now
exactly.
we start isolating it down in sections and breaking out into
Yes,
quadrants.
yes. So that happens, as you said, that happens instantly,
Yeah.
right? When you use the power, it's
And Rob, we'll get to your question in just a second.
yep. So it happens immediately and instantly. So the way we are explaining is like we are, like automatically the system will be divided into 4 quadrants.
Yep.
So that's what it is. So we are showing the 4 quadrants and the importance of those quadrants. Also, we are going to go through. That's why it is important, right? So some OEMs does with the UPS, like ours is a standard Hillphoenix. We do a standard, like a UPS and the battery will be installed on the rack.
Yep.
And some does with the capacitors, and some don't. They don't do it. So it depends upon the manufacturer who does the design. So, and the third quadrant is the medium term discharge. I mean, not medium term discharge, low term discharge, and the medium term suction is your third quadrant. And the fourth quadrant will be the low temp suction and from cases. So it is all the way from the expansion valve to the compressor. And similarly, from the medium term suction side, it is from expansion valve to the compressors.
So if we really look at this, it looks like we're really cutting off. We're going from the compressor as our one line on
Yes.
both sides, medium and low temp.
Yep.
Discharge up down to the high pressure valve. That's our high side quadrant down there. The lower side, we're
Yes.
going from the discharge of the low temp and then working around back to the evaporator side. Then the low side is suction side of the
Yes.
compressors, and then the evaporator side on both medium and then also on the
Yes,
low temp.
exactly. So the quadrant is like, this is 130 quadrant bar, and then this is like 45 bar quadrant. And this is the low temp is like 30 bar quadrant, and then the medium temp suction is also 45 bar quadrant.
So at this, a question came in about if the UPS fails, and this kind of leads to as to where we can isolate it down. So if the UPS fails, that's really looking at the high pressure valve or the flash gas valve bypass. If those wind up staying open, then what winds up, where are we lost in that? Is that do we need a technician then to be able to make it there and realize this? What's our?
Yeah, that's a very good question. So if you lose your UPS, say for example, UPS fails hypothetically, right? So if it happens, right? So if that happens, what will happen is the system will be divided into 3 quadrants instead of 4 quadrants. So now you are exposed to
So just the quadrant just got larger.
yeah, get larger. So you'll have like a more surface area and also more like a system to, like have the liquid and the gas. So what will happen is when the heat transfer happens and the pressure goes up, then you will leave the gas from here and then it goes to the higher side. What will happen is the pressure will be equalized, the first step, because it's not closed, right?
Right.
So now the flash tank pressure will be equal to the gas club pressure, vice versa, gas club pressure will be the flash tank pressure.
And we get into that area of the 45 bar versus the higher bar.
Yes, and also flash gas bypass is also not closed. So now you have only 2 quadrants. I said like 3, but it is only 2 quadrants. So your medium temp suction will be exposed to the same pressure. So the low temp will be still isolated because you have the low temp compressor is separate from that. You already, like have the expansion valve closed, and then up to the compressor, it will be a separate quadrant. And if these two don't close, then all will be like 1 quadrant.
So I guess in a power outage, it's
Yeah.
kind of one of the first things you want to take a look at.
Yes,
You
the
kind of
first
check through.
check the
So
valves.
on
Yes.
site, check those valves. If they're not closed, then
Yep.
hand lever
Yeah.
and
Yeah.
isolate those.
There's a magnetic tool that you can
Or
use
magnet
that
tool,
so you
yeah,
can close
run it shut.
shut, or you can have there's a bypass, I mean, ball valves, you can close it
There are
also.
bar valves too.
Also
right?
close to, yeah, you can make it as a 4 different sections, yes. So the importance for this is we did an analysis on typical supermarket store, which has about like 1:3 load ratio to empty to LT. And then we did a charge calculation, like where all these charges are residing on which quadrant, because that's more important, right? When we come to like a charge preservation, this is very important, where my charge is and which one I need to take care first. So looking at this, typical estimated charge distribution around the system, and the system is, like into four quadrants. High side, medium term discharge to high pressure valve, like stores about like 23 percentage charge. On the system can be 120 bar or 130 bar depending upon the gas flow type. And the liquid charge is 46 percentage, which is from receiver to the expansion valve. Those charge will be like 46 percentage of the total charge. And the medium term suction is about 17 percentage. Medium term suction is from expansion of the medium term cases all the way up to the medium term compressors and the low term discharge line. That's about 17 percentage. And then low term suction will be like 14 percentage. So this quadrant will have like 14 percentage of charge. So why this is important is now you have the 23 percentage of the charge. What will happen in this region or in this quadrant is, the compressor discharge at high pressure and high temperature and during normal operation, right?
Right.
So the temperature can be like 180 degrees or 200 degrees depending upon the ambient, and the pressure can also be from 650 to 1600 psi, right? So when we lose the power, the ambient may be like 95 degrees or maybe like even 98 degrees. So, but what will happen is, since your CO2 temperature is high on those lines, it will come down, it will
Yep.
cool down, and it will, like a close to be ambient temperatures. So the pressure will drop at that time. And even if the temperature goes up, the pressure may increase slightly. And this charge is protected by itself, the high side. So we don't need to worry about the charge on the high side, which is about 23% of your total charge. And then the major charge is 46. We will go over this charge, liquid charge later. And then we did an assessment on suction side, why and what happens on the suction side. That's a more important one. So going into the pressure assessment. So this is a typical simple, like one line diagram of a supermarket showing the cases inside. This is, need to understand this one. Inside the store, the temperature will be like about 72 degrees during normal operation. And then you may have a rack inside a machine room. And the machine room temperature can be like 72 to 85, even a little bit higher based on how the ventilation is provided. And then the ambient will be like a room temperature. I mean, ambient temperature will be on the roof will be different than whatever we have here. So this equipment location, if it is an indoor. And if you go to the other equipment location, it can be an outdoor location where the rack is on the roof, and the gas will be on the roof, and the receiver will be on the roof, and then the liquid and the suction piping coming to the cases. So the case on the sales floor or the like system store design will be like 72 degrees when at the time of power loss. So how and so this so the analysis is the assessment that we did. We took an evaporator and a liquid line and a compressor, right? So this is on the medium term suction side, on the low term suction side. So we'll
Okay.
go over this first before we get into liquid side, why we didn't, why liquid is important and why suction and how the suction plays into the charge preservation. So this analysis only carried out on the evaporator section, and we excluded the the lines at the outlet of the evaporator to the compressors because it's already superheated gas. So based on the quality, when the CO2 liquid enters sorry about that, enters from the liquid line to the expansion valve. So right at the expansion valve, the vapor quality for the medium temperature evaporator is 0.07. And the vapor quality right after that expansion valve is 0.22. So why is that the vapor quality is, like different? So the pressure we are dropping from, liquid pressure is about 515 psi, and then
Yeah.
we are dropping to only like 400 psi, dropping to
Small
400,
drop. Yeah.
small drop, and then the vapor quality is, like less for the medium temp. Whereas the low temperature, we are dropping, like 200 psi or 250 psi, right? So when you drop it higher, then the vapor quality starts, high.
Especially in higher.
Yeah, higher vapor quality. So based on this vapor quality, and then the like liquid vapor mixture enters and flows through the coil and it evaporates, At the end of the coil, your vapor quality will be 1, which is all the liquid boiled off, it absorbed heat, and then it's going out of the
Yeah.
coil,
Fully saturated, making
fully
its way back.
saturated, way
Course.
back to the compressor. So at the, like at the outlet of the coil, it will be running at 10-degree superheat, 10-degree superheat.
That's
And then,
cool.
yeah, and then by the time it reaches the compressor, the superheat will be, it's a superheated gas. So the return gas temperature for the low temp will be 40 degrees, and the medium temperature will be like 50 degrees. So we excluded this portion of
At the suction line header at
at
the
the
end.
suction line header.
Okay, back to
Yep.
the case. Okay.
Yeah, back to the case. The reason for that is it's already a superheated gas, and there is no liquid droplets for expansion.
Right. It's dry.
So it's dry. So that's why we excluded that analysis. And also this side is completely liquid, and the vapor quality is 0, and the expansion will close. And this is separate section of the system, right?
Yeah.
Separate quadrant. So we took this and we looked at the average vapor quality on low temp and also medium temp evaporators. So low temperature evaporator, the vapor quality is 0.5, which is 50% liquid and 50% vapor average. And this is during normal operation, right? At the time of power outage, this is what you're going to see. For the medium temperature evaporator, it's close to, like 0.45 percentage of, so 45% liquid and 55% um, 45% vapor and the 55% liquid. So that's how you see it in the normal operation. When you lose the power, that's what you see it immediately at that time. So with this analysis, and we did, test this in the lab. So we took the pressure volume chart to see what happens after the power outage, right? What will happen after the
And
power
our,
outage?
and our main focus for this is to evaluate the liquid that's in the evaporator and how far we're going to actually expand and whether we're going to hit that point or not.
Yes, exactly,
Okay.
exactly. That's what yes. So when you look at the analysis and also how it operates, is like now it becomes a constant volume. It's a fixed volume, right? So the volume doesn't change, but your temperature is going to change based on the heat gain.
It's going to change it.
Yeah, and then based on the temperature change, your pressure is going to increase.
Mhm.
So we start at this operating condition. For this example, we start at like like 0.1. The 0.1 is like 17 degrees saturated suction and pressure of like 14.7 and 213 psi. This is like a low temperature evaporator. So this is where we start when we lose the power. And then to reach to 0.2, the 0.2 is like relief valve setting in the system design. So we looked at 30 bar, right? So we looked at the 30 bar, and the temperature has to increase to 29 degrees to get to 30 bar.
Okay.
So if you look at the room temperature or the stored inside temperature, because the evaporator is inside the store, it's air conditioned, it is 72 degrees and at the time of a power loss, and the temperature has to increase like 46, degrees Fahrenheit to get to 30 bar.
Right.
From,
yeah,
like
because
from
you're-
minus 17
because
to
you're
29,
negative
right? So
17, maybe, yeah, to get to that point, you've got
that's a-
that much of a distance plus all the product that's still in there that's
so there's
maintaining
a
that
maintaining
temperature
the
at that point
temperature. So
too.
it takes like hours. It may be like 5, 6, 7 hours to get to that point on the low temperature side. To reach to 0.3, which is here, the temperature has to go to 173 degrees to get to 45 bar.
45 bar.
45 bar. So on the low temperature evaporator, it's impractical to get to 173 degrees in the store unless there is something going on, hurricane or fires or something like that.
Right.
So during a normal power outage or during a service event, there is no way you get the temperature to like 173 degrees inside the store. So that's one of the reason, it is okay to stay with the current design, like a 30 bar, or maybe like if you want to go to like 45 bar, that may be another option. But that's why we say like, I stay with like current design. So
And that was the 14% of the charge too.
yeah, that's also 40%
So
of the
this is
charge.
the lower percent of the charge that we're talking about and the quality of liquid and then what it takes to get to a point where we're actually going to trip and relieve that 45 bar
Yes.
is quite low.
Yes, very
So
quite low. Yeah.
That's
The risk
the
is very
study that
less.
takes us down that path.
Yes, that takes it down, but yeah, the risk is very low. So, and similarly for the medium temperature evaporator, right? So we did the same analysis with the constant volume, and we start with the 0.1, which is 22 degree, SSD, saturated suction, and then pressure is about 29 bar and 420 psi. So that's the 0.1 when we lose the power. And by the time we get to 0.2, which is 45 bar, that's what the relief valve is set to on this design. And the temperature has to go to like 50 degrees, 50 degrees. And then to get to 0.3, which is 60 bar, if you go to 60 bar, then the temperature has to rise like 90 degrees approximately. So even on this case, like you started like 72 degrees store temperature, it takes hours to get to first 45 bar.
Switch over to 60.
Yeah, switch over to
the
60.
issue.
Yeah, it gives you like a lot of time. So
it kind of speaks to like Rob question. You had a great question that came in about, hey, when we're gonna start using systems with high pressure ratings at the evaporators, when we're gonna start seeing that higher, 90 bar larger pressure rated systems at the evaporators. Well, we always want to do something with good knowledge and education and matrix based around why we make these decisions. And when we look at this and see that in the low temp, we have to go this far to even get to a point at 40% of the charge. And if we take these studies, we see that we're not so sure that it's worth the investment of the larger systems at the evaporator when there's other opportunities to take versus increasing that cost. But we will talk more about the larger 90 bar options and other systems towards the end.
Yes. So we are going to look at that one as one of the mitigations, right?
Yeah.
What are the types of mitigations we can go through that? So we'll go through that. And so there's one more point that we wanted to make why liquid is important. And when you look at the new popped up here, so the liquid approximately starts at 560 psi pressure. It might be sometimes 530, 550. So for 20-degree temperature rise, going from like 40 degree to 60 degree approximately on the liquid temperature, the liquid pressure goes to 180 psi for 20-degree temperature rise.
Okay.
Whereas for the vapor, same 20-degree temperature increase, the pressure is only 60-degree increase. So it's very minimum, right? So that's why we
all sensible, not really doing anything.
Yeah, not doing anything. So that's why we say like, okay, for the vapor, you will have like more time. Like even if you lose the power before the pressure hits the relief valve, you will have like, hours, 6 hours, 8 hours, 10 hours, depending on the location and, like ambient conditions. So, but for the liquid, if the receiver is outside on the roof, it may be, like the pressure can go quickly up, the temperature can rise, right? So that's another thing that we are going to look into the mitigation, how we mitigate that. So, different approaches. Different approaches to mitigate the increased pressures. So the first option, this is our standard design, and then there's second, like this is the 130 bar on the high side, but this can be like 80 bar or 90 bar system design. We put a question mark. It can be 80 or 90. So what are the changes that we have to make to get on a like 90 bars or 80 bar system design, high pressure system design, right? So that's more important to understand. On the rack side, it starts from the pressure vessel. This needs to be 90 bar or 80 bar component, and then all the pipes that we need to do on the store side also needs to be like a 90 bar or 80 bar high pressure copper, or it can be a stainless steel. And the low temperature compressor needs to change. All the cases and it needs to change. Cases meaning like evaporators and the piping inside the case needs to change to high pressure component. Expansion valve needs to change. Similarly on the medium temp, and all the piping in the rack needs to change. Relief valves has to change. So, and of course instrumentation needs to change. So these are the major change that needs to happen both within the rack and also within the store. All the components need to change. So if we make all these changes, we can do like 90 bar. So, like there are certain companies, they do 90 bar. Also, we do 90 bar as well.
Yeah, we have some industrial companies that do 90 bar and see that.
Yeah.
And, from talking with them that come in for some of our classes, they say that they're looking at, 25, 30% increase, from system to system when they go to that full length with materials. And then there's a time function too. It's heavier, it takes longer.
Yes.
Everything struts, everything has to be rigged to accommodate that, plus the refrigerant itself. So those are all the considerations, right?
Yeah, and then some of the other things also, like some of the supply chain is limited as well, with respect to 90 bar. Not everybody has caught up to 90 bar yet. So some components are limited.
Codes, whether they allow the copper, whether they want stainless, how they want to do that, how they want it fitted, how they want it jointed.
Yeah. So those are the considerations we need to consider when we go for think about like 90 bar system. So what are the other methods, right? There are two more methods we can go through. This one is one one of our old designs. Still many other OEMs does. So this one charge, like preserves about like 70% of the charge, especially on the liquid side. So what this design is, this will have a heat exchanger connected to the flash tank, that pulling the gas at the top and condensing it at the bottom, the heat exchanger. And the condensing unit will be like HFC, HFO condensing unit. This is very, for condensing. So what it does when we lose the power, so this condensing unit pulls the gas and condenses the CO2 and keeps it, like a charge within the system. Keeping the pressure maintained within the system below like leaf valve pressure. So it preserves the whole liquid charge, because when we lose the power, all the valves will be closed anyhow. Same four quadrants, and it preserves the liquid charge. So, and also the high side will not like impact, because it's already high pressure, it comes down. So this design using an auxiliary condensing unit, the only kind of disadvantages is like this uses HFC and the HFO refrigerant.
Right.
So that's only kind of
And
disadvantage.
you're also locking off the quadrants. Nothing else is moving, nothing is being removed. So
Yep.
depending on what happened, how much liquid is actually in the low temp case, how much liquid is actually in the evaporators, medium temp, whatever that looks like, it is what it is.
Yes.
And then heat goes to cold. So you're just creating a cold environment. It's going to slowly migrate its way, and you're just going to keep that temperature and flash tank down to a certain level, and it'll just buy you more time.
Yes.
That's what it
Yeah.
winds up doing.
Yeah,
But
exactly.
if in this scenario, if the low temp cases or the medium temp happen to be flooding prior to it happening, or whatever that case may be, where there's a lot more liquid in that, this isn't going to remedy that.
Yeah,
It's
remedy
not
that.
going to, it's just,
Yes. Yeah.
it's trapped where it is.
Yeah. Yeah. Exactly. Yeah. That's right. And the next one is using a CO2. So this is like a charge secure, the name of the technology. But the advantages of this one is like this uses a CO2 refrigerant from the system, and also it uses the same oil from the system, and it maintains the flash tank pressure, and also the medium temperature. Medium temperature. So it pulls the gas off the receiver, and goes to the compressor and compresses and put it back on the gas cooler. And then when the gas flow pressure increases, it recirculates back into a flash tank. So a simple gas recirculation system designed to work with the, like a CO2 booster systems, and using the same CO2 and same oil from the rack. And this preserves about like 70% of this charge, since it's isolating the suction sites, and this charge, this preserves the liquid side, the whole liquid side, and also on the high side too. So this is also very simple design that we implemented recently, and we have a lot of tractions on this design, because it's a natural, and it's also very tiny compressor. It uses like a small 400-watt compressors.
It's integrated or
integrated.
system.
It's already integrated in the rack itself, so it helps to preserve the charge.
No regulations with HFC.
No regulations, exactly. So these are the kind of, like three methodologies, like to mitigate the pressures during power loss, and also service events, any service events for a longer period of time. So it helps to charge. And charge secure uses a battery power, a UPS and a battery power. It comes with the 1, 2, or 3 batteries, depending upon the, like a number of hours you want to protect your charge. And also it can be powered by a generator as well. So it's a very sleek and small design. So with that, I think.
Question came in, Robin. We use the CO2 condensing units. Do you mean like for the actual application? It's not necessarily a condensing unit that we're talking about here. It's a separate system that's designed and built to run with a fractional horse compressor and utilized with a UPS that's integrated into the system.
Yeah.
If you're asking if we've experimented with smaller CO2 condensing units, I don't know if we have, but
No, we have not.
they run a little longer, they're a little larger, they have a little more power usage to it, and then you'd have to have something, a generator or something back up to operate that compressor to kind of do the same thing.
Yeah,
So,
yeah.
Yeah, I think this question came in when you were talking about the auxiliary condensing unit.
Yeah.
So yeah, thanks so much for catching that.
absolutely.
Yeah. Thank you for listening.